Hello. Let's start our review session today. Today we are gonna today we are going to review the homework, the solution of the second homework. So let's look at the homework. First, let's look at the homework one. Suppose you are a private craftsperson specializing in customized baby cribs. Expectant parents place their orders with you and can choose from a wide range of options or even come up with their own unique design with your help. You build the cribs on a first come, first served basis. So first come, first served basis. Demand is random and you get an order every four days. So the demand coming in every 4 days on average. So we can know the demand rate is 1/4, right? Due to the custom nature of the red cribs, it takes on average 3 days to build one. 3 days. So we know the service time is 3 days. And you can assume that both the demand and time to build a crib are exponentially distributed for your analysis. So we know we can use the equations to solve the problem. So first, let's look at the first problem. A new customer has called and wants to know how long, on average, a person has to wait from the time a crib is ordered until it is finished. What do you tell the prospective customer? So basically, from this question, we know that we are required to calculate the time, the wait time in the system. And let's look at the formula to calculate. Hi, welcome. So I am about to calculate the first problem's question A. And let's look at the formulas. So for question A, we need to calculate the average time in the system. So we need to use this formula, right? W is the average time equals 1/mu minus lambda. Mu is the service rate and lambda is the arrival rate. So let's write it here. So lambda is the arrival rate, which equals 1/4 cribs per day. And mu equals 1/3 cribs per day. And we know how to calculate the average wait time in the system. Average time in system, which equals 1/1 mu minus lambda. And this equals 1/1/3 minus 1/4. This equals 12 days. So we would tell the prospective customer that the wait time from you place the order to you can get the crib is 12 days. Then let's look at the second problem. What is the percentage of your time is spent working on cribs on average? So this is to ask the utilization of the whole system, which equals lambda over mu. Lambda is the arrival rate and mu is the service rate. This equals 1 over 4 over 1 over 3. This equals 75%. So 75% of the time you work on the crepes on average. Next, you don't really have an inventory tracking method, but all orders are put into the basket in the order they are received. When you begin a new crepe, you take the order out of the basket to use in the shop. Lately, it seems that the orders keep piling up. How many orders do you have in the basket on average? So the orders you have in the basket is basically the number of people in the queue, right? So it's the queue length. How to calculate the queue length? We can use the formula from above, from here, not above. Queue length, the average number in line equals rho. Rho is the utilization times lambda over mu minus lambda. So average. Yeah. Average number in queue equals lambda over mu times lambda over mu times lambda over mu minus lambda. And this equals, so since we know lambda over mu is the utilization and we have already calculated, so it's 0.75. And lambda here is 1 over, so lambda is 1 over 4 divided by mu minus lambda, which is 1 over 3 minus 1 over 4. And we, after calculation, we got this equal to 2.25. And this is the 2.25 crepes per, yes, no per, it's 2.25 crepes on average. We have 2.25 orders in basket. Okay, next let's look at question 2. You are asked to help the Port Authority of Long Beach to predict the performance of a new container facility. The proposed facility has 3 berths, so have 3 berths that operate independently and can each unload and load a container ship in 6 hours on average. So the 3 berths serves like the number of servers, and then the 6 hours on average is the service time, and it follows the exponential distribution. Since ships have to be turned around as fast as possible, the facility will operate continuously 24 will operate continuously, like it's 24 hours per day and 365 days per year. So ships arriving at the port will first wait in the harbor and then be assigned and directed to the next available berth on a first come, first serve basis. The Port Authority predicts that initially 70 ships per week will attempt to use the new facility. The actual arrival times of ships are unpredictable, but historical records show that the time between arrivals tends to be exponentially distributed. Let's look at the first question. Describe the queuing model that you can use to analyze the performance of the proposed facility. So first, let's look at the example from the class, how to describe a queue model. So we know the MM1 queue, right? So we use the first M here is the arrival, so describes the arrival type, and the second M here describes the server type, and here, one here represents the number of server. So based on these rules, we know for this problem, we have Markovian arrivals as well. So here is M, and we have Markovian servers as well, which is because the service time are exponential too, and we have three pairs. We have three pairs in this port, so we have three server here. So we can describe the queue as I'm 3Q, and the arrival rate with arrival rate lambda equals 70 per, let me see, 70, it should be 70. Yeah, 70 ships per week. And service rate equals, let's see, service rate, since the ports can operate independently and each unload and load the container ship in 6 hours on average, and they operate 24 hours per day. So we know they can operate 24 divided by 6 per day. Since our arrival rate is in ships per week, so we times 7, then we got 28 ships per week. And this is our service rate. Next, let's look at question B. Estimate the average time a ship that is served spends in the system. So we need to calculate the wait time in the system. And since we know it's an MM3Q, we don't know how to calculate the problem by hand. So we use the Excel. And we put the arrival rate here, 70. And service rate here, 28. In number of servers, we put it 3 here. So we know. So we know the expected total time in system is about 0.0859.
Johan, we can't see the Excel spreadsheet. Well, I shouldn't say we. I can't see the Excel spreadsheet. It looks just like a black box.
Oh, okay. I'm sorry. Let me see. Let me see how to share this. Can you see it now?
Yes, perfect. Thank you.
Okay. So let's start from here. Arrival rate is 70 and service rate is 28 because we just calculate that, and the number of servers is 3. So we put all these numbers here, and what we want is here the expected total time in the system, and we got the answer here, and its point is 0.0859. So stop share. Let's yes. So we know the ship that serves spent average time. The average time a ship spent in the system equals approximately 0.086 weeks, and you can calculate in hours. It's roughly about 14.4 hours, and this is from the Excel. So next, oh yes, I have it here. Next, let's look at the third question. The Port Authority expects the number of container ships that want to visit Long Beach to double in 7 years. So meaningless here. Also, the Port Authority would like to achieve a service level of no more than 15 hours on average spending in the facility for a ship to unload the cargo. How many berths will be needed in 7 years to achieve this service level with the additional demand? Let's look at the Excel sheet. So I'm sorry, the Port Authority expects the number of container ships that want to visit Long Beach to be double. So here it's doubled, means the arrival rate will be 2 times. Will be 2 times the previous one, which is 70 equals 140 ships per week. And the Port Authority would like to achieve a service level of no more than 15 hours on average spending in the facility for a ship to unload the cargo. So let's look at the Excel again. Which is oops. So we put the arrival rate 140 here, and we found this line, right? The arrival rate should be less than the overall service rate. We found that utilization is way more than 100%. So since we know the utilization should be less than 100%, and we can add it to 4. Let's see, it's 125%. No way. 5 then it's 100%. But we cannot have a utilization equal to 100%. Then we increase some more. Then this should be good because it's 83.33%, and we have the wait time in system, which is this. So from the Excel spreadsheet, a total of 6 birds will be needed in 7 years to handle the increased traffic with the desired service level. Okay, so that's all for today's homework. Any question?
No, thank you.
Thank you so much. Then I'll stop here.
Okay.
See you.
When do you think you'll be able to post the video?
It'll, I think in about a couple of minutes.
Perfect. Thank you so much.
Thank you. Bye.
Bye.